Hi friends, we're going to take a look at a problem from Chapter 5 that is a Newton's universal law of gravitation problem, the kind of problem that astronomers might encounter in their work looking at neutron stars. This is page 132, number 36. And it goes, a certain neutron star has 5 times the mass of our sun packed into a sphere about 10 kilometers in radius. And they ask us to estimate the surface gravity on this monster, is how they put it. So we're looking for the value of G right here. Now this is indeed a monster. Neutron stars are very interesting because all of the matter within them is neutrons. There are no positive or negative charges that can repel, and so you can pack them much, much, much more densely than you could pack atoms on Earth. And in particular, we have 5 times the mass of the sun packed into a relatively small volume of only 10 kilometers, or 10,000 meters. And we're supposed to find the value of G here. Now, here's the idea. If I take this object that's at the top of the sphere in red, and it has a mass of m, then the one force that's pulling down on it is going to be the force of gravity. And if I write that force of gravity as mg, where g is not 9.8 meters per second squared, but is whatever g is on this star, then these two forces obviously have to be equal. In other words, mg has to equal the force of gravity, which is g, times the mass m, times the mass of the star, divided by the square of the center-to-center distance between them. And it's pretty obvious that the mass m cancels out, so that I get an expression for the acceleration, which is g times the mass of the star divided by r squared. Well, the mass of the star is 5 times the mass of the sun. And I look up in the front of the book or on Google, and I find that the mass of the sun is 2 times 10 to the 30th kilograms. So that 5 times 2 times 10 to the 30th is 1 times 10 to the 31st kilograms. And I now have all the information that I need to plug in. We're going to get 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times 1 times 10 to the 31st kilograms divided by 1 times 10 to the 4th meters, or 10,000 meters squared. And actually, we can do this computation in our head, because the mantissa is 6.67 times 1 divided by 1, which is 6.67. And the exponent is going to be 10 to the minus 11 plus 31 is 20 minus 8, which is 10 to the 4th squared. And so that's going to be 20 minus 8 is times 10 to the 12th. And the units are going to be kilograms cancel and meters squared cancel, so that I get newtons per kilogram, which, as you know, is a fancy term for meters per second squared. This is indeed a monster. Compare this to the gravitational pull of the Earth, which is 9.880 meters per second squared. And you can see that this is approximately 1 trillion times as much gravity as we would have on the Earth. If you were to stand on this neutron star, you would not be squished so much as pulled apart, because the gravity at your feet would be greater than the gravity at your head.